Okay, my dear students, today let me solve some of the few selected exercises which I assigned you. Now this is the solution on this page of my notes. This is the solution of this particular exercise, exercise 6.2.5. Find the analytic function omega z is equal to uxy plus ivxy if u is equal to this part A and if v is equal to this part B. So in either of these parts, real or imaginary term is given and we have to find the other term. So let's go to the solution of this problem, of this exercise, which is very simple. So here I have solved this. So you see that u is x cube minus 3xy square, and now because the function is analytic, then we have to satisfy the CR conditions. So this is the CR condition, partial derivative of u with respect to y, which we obtained from this given value of u is minus 6xy and minus 6y, and second derivative of u with respect to y square is minus 6x plus minus 6, and because this is the Laplace's equation, we have to show that this equation is being satisfied, and you can easily prove this. It is done over here, but now let me solve to find the value of v. These are the CR conditions, and from these two conditions we obtain the differential of v equal to partial v by partial x into dx, partial v by partial y into dy, and this is equal to, by CR condition, this partial v by partial x is minus derivative of u with respect to y. So we have replaced the CR conditions here, and now we have calculated the value of dv, as you can see as over here. So from dv, when we integrate, we get the value of v, and here is this constant, and this constant is also determined as you can see from here. So this is the solution of the part A of this exercise, exercise 6.2.5, and on similar lines you can find the solution of the part B. So that was the exercise and its solution 6.2.5. The next important problem I have selected is 6.2.8. Here we have to derive the CR conditions in polar coordinates. So these are the CR conditions in polar coordinates, where capital R is the real part and capital theta is the imaginary part of the given function. And let me see where I have solved this equation, somewhere here from my notes. So let me display before you the solution of this part, the derivation of the CR conditions in polar coordinates. Okay, this is the detail. This page is so don't mind about the exercise numbers, they are different as compared to the edition third of. So here is this solution. So you can go to this problem 3.11 mentioned here, and you go through this derivation and you will find the derivation of the CR conditions in polar coordinates. Okay. Okay, the next problem I want to discuss is well, the rest of the problems from this exercise you can try yourself, and you can even find the solutions of these rest of the problems from this exercise from my notes. So you just turn over the pages of my notes and you will find the solution of the other problems. Now let me go to the next exercise, which is exercise 6.3. This is the one. So here I have solved some assigned problem from my notes. For example, this problem, exercise 6.3.4, you can find the solution from my notes and very easily, and you can go through the solution. Let me now jump to the next exercise 6.4. Okay, so this is the exercise 6.4.1. Show that z minus z naught power n dz integral is 2 pi I when n is equal to minus 1 and is equal to 0 if n is not equal to minus 1. So this exercise has also been solved on the pages, and this is the next exercise 6.4.2 to prove that 1 over 2 pi I integral contour integral z to the power m minus n minus 1 dz shows the Kronecker delta function. Now this is an important exercise, and let me see if I can show you the solution from my notes. I have solved this problem somewhere. Well, you will find the solution from my notes. Let me find it for you. So this is the exercise I have shown you. Here the number is different, but don't mind this exercise number over here. But this is the integral. We have to prove that this integral is equal to the Kronecker delta function, and we take the first case. If m is equal to n, then I is equal to 1 over 2 pi I integral z to the power minus 1, and we write z in the polar form r e to the power I theta, and obviously dz will be r I e I theta d theta. Substitute the values and you get this equation, and then continue with the further steps, and you will easily see that the result of I is equal to 1. And the second case, if m is not equal to n, you can show that if m is not equal to n, then m minus n is not 0, and therefore z to the power m minus n minus 1 will be analytic, and you know that the integral of an analytic function around a closed path is always 0. So we have using the Cauchy integral formula. So we have proved that if m is equal to n, the value of the integral is 1, and if m is not equal to n, the value of the integral is 0, and this is the property of the Kronecker delta function. Okay, now let me move on to the next exercise. You can find the solution of this exercise and the solution of all these assigned exercises, but this exercise is very important. Show that if exercise 6.4.7, show that the nth derivative of a function z naught, the absolute value is less than or equal to capital M n factorial over r to the power n, where r is the radius of a circle centered at z is equal to 0, and m is the maximum value of f of z on this circle. So assume that f of z is analytic on and within the circle. So let me find the solution from the pages of my notes. Okay, let us see if I can find the solution of this exercise. I think I have skipped this. It is somewhere solved here on these pages which I have already sent to you. Let me find it for you if I can find, otherwise you can see this yourself somewhere on some page. This exercise is solved. Okay, so this is the solution given on this page. So please go through this derivation and you will prove that this exercise, this one. Now this is proved on the page I showed you. This is known as the Cauchy inequality. It is very important inequality. This result is known as the Cauchy's inequality. Okay, we will use this Cauchy's inequality in the next exercise 6.4.8, that if f of z is analytic and bounded, then f of z is less than or equal to m, a constant for all z. So if the function f of z is analytic for all z, then show that f of z must be a constant. Now this is the statement of Liouville's theorem. So please try to digest this statement. We are given that f of z is analytic and bounded for all z, that is for the whole entire organ plane. Now this is only possible if the function f of z is a constant. So what we have done to solve this exercise is very simple. Over here I have solved it somewhere here. Okay, here is the solution of the Liouville's theorem. If f of z is analytic and bounded, then f of z absolute must be less than or equal to some maximum value for all z. Show that f of z must be a constant. So here is the proof. So we have taken the nth derivative of f of z less than or equal to mn factorial over Rn. This is the Cauchy inequality which we derived in the previous exercise. Now if we take n is equal to 1 and z naught is equal to z, we can write this as the first derivative of the function at z equal to less than or equal to m over r, because n factorial is 1 factorial, which is 1, and this power is also 1. Okay, so this is so if r tends to infinity, obviously the first derivative will be equal to 0, which means that f of z will be constant. So this is a very important and useful exercise I have discussed now, and the rest of the exercises you can find the solutions given on these pages. So that's all about the solutions of the problems enlisted to you from chapter number 6. So in the next lecture I will discuss the solutions of the problems on chapter number 7, which I have already assigned to you. So let me finish here, and then in the next lecture I will talk about the solution